All right, so we continue with the short talks, and our first speaker is Yang Hui He.
Thank you very much. It's a pleasure to be here. Thank the organizers. So actually, thanks to Liam's beautiful talk, I think all of the physics talks can be shortened in their slides. So just briefly, this is based on some work with some of which with a lot of people here, and a shameless self-advertisement for an upcoming book with Springer. So Liam spared me of trying to explain this landscape. So basically, the thing I want to emphasize within this, as Keith pointed out, within this corner of the geometric compactification scenario, there is actually a dictionary where physicists can use to talk to algebraic geometers and differential geometers. So the point, for example, if you take the heterotic string context, you're given very precise data, for example, a Calabi-Yau threefold, some polystable Hermitian equivariant bundle. This is a lot of stuff we've been doing with Andre Lucas. And then everything brown here is the physics, and everything here in black you can go take to a card-carrying algebraic geometer and explain to him or her this is what you want to actually compute. So this is the compact Calabi-Yau threefold landscape. So the one that Liam talked about is this biggest one by far, this Kreutzer-Schacke data list of about 500 million data points. The oldest construction, the first construction of Calabi-Yau threefold is the quintic, the degree 5 homogeneous polynomial in CP4. And then there are various other ones like elliptic fibrations, which is what his favorite ones. And and various works have been done just to identify which of these are and where. So here is actually a log heat density plot of the Hodge pair number. So there are about 10 to the 10 Hodge pairs, but only about 30,000 which are unique. So most of them there's a lot of heat down here where the typical Calabi-Yau threefold in this landscape is focused. So in principle, as I think we've encountered in the previous talk, in principle, you could take this. This is now a very well defined set of problems in classical algebraic geometry. You could run your favorite SAGE program or Macaulay 2 program and then try to compute these things. Typically, things like computing bundle cohomology over Calabi-Yau. And the problem is, one, even this Calabi-Yau threefold landscape is far too large for this brute force attack. And secondly, which is sort of the biggest hurdle in computational algebraic geometry, is that the core algorithms are, for instance, Grosvenor basis computations, triangulations, are all exponential running. Right? So this is where the machine learning comes in. You just take, people have been doing, many people here, have been compiling these results for the last 40 years. Is it possible to set up clever neural networks or machines to try to guess quantities? Right? So this is just, there's not very much time. So can you guess at topological invariance instead of actually doing this by brute force, by chasing sequences? Right? This is what you do in algebraic geometry. You chase non-exact sequences. Intuitively, this might work because problems in algebraic geometry over C is, as I said, just chasing this, and it essentially reduces down to finding kernels and co-kernels of integer matrices. Again, your input data will be some integer, and your output, a list of integers, and the output would be some kind of integer invariant. So just to give an example, so this, you could find even some simple multilayer perceptrons would do pretty well in actually guessing. You have no idea why it's doing this, and it would be very nice to ask mathematicians, how do you predict conjectures why the machine is doing better than traditional methods. Right, so here's just an illustration of a particular thing. So this, of course, distracts me on a bigger problem, which is very much in the spirit of what Mike was talking about, which is, which branches of mathematics are actually amenable to machine learning. Right? So experimentally, I've tried this one, cohomology computations, and Liam and friends are talking about triangulations. So these kind of problems are good. Problems in finding Kähler metrics, which reflect Kähler metrics, are good. Representation theory, that's what I've been doing with Minyoung Kim. That seems pretty good. Number theory seems pretty bad. I try something as stupid as this. It would be very interesting. Is it even possible to find a neural network that can predict the next one? So in the breakout session I'll have with Sergey later, we'll probably discuss a little more about this. Thank you.
All right, next up is Cody Long.
All right, hi everyone. First, I want to thank the organizers. This is based on work with Jim Halverson, who is one of the organizers, which I believe gives me an extra 15 minutes or so to speak. So Liam and Mike both really set this up nicely, so I don't need to introduce this too much. But as we've seen, the string landscape, this set of solutions is absolutely enormous and is generally computationally complex. So even with general theorems about quantum gravity, algebraic geometry, we're still going to probably need to take some sort of statistical approach to understand global properties of the landscape. One thing that Liam alluded to was that most string vacuum, most of these effective field theories coming from string theory, have large numbers of fields n. In the Kreutzer-Skarka ensemble, the one that Liam concentrated on, this number n is of order 491. But in some other ensembles that are well known, such as the BMAX geometry from Wadi and this tree ensemble that Jim and I, along with Ben Sung, constructed, the numbers are 1,800, for instance, for the number of axions, number of fields, and all the way up to around 300,000. So there's been a lot of progress in understanding these some certain aspects of these geometries and accounting of vacua, but I still think we're going to need a statistical approach. So one of our goals is to determine a distribution of physical quantities at large n. So this will denote omega, and these physical quantities are O. So how do we actually write down these effective field theories coming from string theory? Well, after you've specified your field content, which are these fields phi, well, you write down the scalar object called a Lagrangian, which tells you all about your physical theory. So for instance, you have distances on field space captured by some metric, Gij, you have a mass term, Hij, and then you have all sorts of interactions such as Yukawa coupling,Cijk. So this theory, besides being specified by the fields, is specified by tensors, which are often determined by geometry. We can construct many examples, but only an infinitesimal fraction of the total set can actually be constructed and studied in a given finite time. So, in addition, examples at large n are relatively expensive to construct. So, one question I'd like to ask is the ensemble of tensors well approximated by some random tensor theory? I.e., can we take the entries of the tensors drawn from some simple, relatively simple distribution, which would make life a lot easier to study at large n, because then we wouldn't need to do these geometric computations. We would simply study the statistics of these ensembles. So one simple example, well, this G that I wrote down, this is a metric, it's a Kähler metric. And the question I want to ask is, can we approximate it as some sort of random matrix? So our goal, overall goal, is to determine the random matrix theory for geometrically derived Kähler metrics at large n. A simpler goal, one that's probably more attainable, is to obtain a model for Gij at small and intermediate n, when we can actually gather some data, and extrapolate to large n and ask statistical questions about the landscape using this statistical model. Okay, so the main idea is to use machine learning to determine this random matrix theory model. Liam and I tried in 2014 by hand, and it was very, very difficult, so perhaps machine learning can give us a new insight in doing this. So one approach is reinforcement learning. Our measure of success, well, we wanted to reproduce some physical quantities, so the game we're going to play is to try to reproduce the eigenvalue spectrum of these Kähler metrics. Now, one technical point is that there's a really nice class of Kähler metrics called Bergman metrics, and this, so I can write this metric as two derivatives of some function. This function is specified by a couple of vectors s, which are fixed by the geometry, and then this matrix p. This matrix P is positive definite. I can write it as a Hermitian square of a matrix. And so what I'm going to do is I'm going to take the entries of this matrix to be drawn from some distribution with set means, but I'm going to allow the variances, the standard deviations, to vary. That's the game we're going to play. So the random matrix theory is specified by these standard deviations, sigma. The nice thing about these Bergman metrics is that any Kähler metric can be approximated to arbitrary precision by some Bergman metric. So we expect that if we're very clever in choosing these distributions, we might be able to get this to work. So a few technicalities. We're using an A3C to explore the possibilities with reinforcement learning. The state space are these variances, and the steps are to change these variances. We change the variances, we sample from a distribution of metric eigenvalues of this random matrix theory, and then we try to compare it to Calabi data and see if we get anywhere close. The reward function is given by the distance, some statistical distance between these distributions. There's a few different ideas that we have to use it, but right now we're using something called a cosine distance. Right now, we've just looked at small h11, h1 equals 15, but in the future, we want to increase this to larger h11. So just a quick plot of some of the results. This green is the null RMT model, the null Bergman metric, and the yellow is the Calabi-Yau data, and the blue is the best state the RL found. And you can see that this is a log plot. The null RMT model was very bad, but it got quickly shifted over by the RL found a very good state that pretty well approximates the Calabi-Yau data. So I'm quickly running out of time, so I just want to state the central idea. Perhaps ML can reveal independence of string theory data, which might allow us to understand the landscape statistically. And I have some questions for all of you that I'd love to talk about if you have time. Thanks.
All right. Thank you.
All
right. Next up is Brent.
All right, thanks. So if you find anything I say in the next 5 minutes interesting, download these slides. I'm not going to really go through them because I think it's more than I can do. But fortunately, Liam already went over this. So I'm going to try to, if you didn't hear what Liam said an hour ago and you weren't really sure how many triangulations are in this Kreuzer-Skark database, could a machine tell you how many there are? That was our goal in a paper we wrote with Jim not long ago. So we know that there are 500 million of these things, and the number of triangulations grows pretty rapidly as you go up, and we have complete data up to this quantity h1 equals 6. This was all done, by the way, on Microsoft's cloud. So thank you, Microsoft, through an NSF grant. So we can't do this by brute force. Trying to get all the triangulations of a polytope starts to crap out on you when you get to h1 of 25, and we got to get to all the way 491. So we wanted to train the machine to do this. The way we approached it was to take these four-dimensional polytopes and break them down into 3D faces and then triangulate those. That breaks the problem down by an order of magnitude. So there's 46 million of those. There's actually 7.5 billion of these guys, but only 46 million of them are unique. And then we're going to take the products of them, just a naive product, and estimate the number of triangulations from that. We know a fair amount about these guys at low H11 value. So up through 11, we had triangulated all the 3D facets that appear up to 11, and a fairly good subset for 12, 13, and 14, and then we start to lose. Okay, so this is the problem I'm going to try to address. We knew the number of these guys was astronomical. In fact, astronomical is not even a good enough adjective for it, right? Because 10 to this number is bigger than anything astronomical. But we only have a lever here of a tiny fraction, 1% of these. And I want to extrapolate from a number that's, let's say, order 10 to the 6 to some number that's 10 to the very large number. Why would I ever think a machine could do this? Right? So let's see if it can. So we started this project with my student with a simple, basic pedestrian neural network. Right? Here are the properties. We gave it 21 different geometrical properties of these 3D facets, threw the kitchen sink at it. We're going to calculate the mean absolute percent error. We're going to train up to 11, and then we're going to test on 12, 13, and 14, then let it rip and see what happens. Okay? Here's what happens. Okay, so we get a pretty good mean percentage error. But then when we extrapolate up to 12, 13, and 14, not only does the error grow, but you can see it's the prediction is offset to low values. In other words, it consistently underpredicts. Not a surprise. This is a classic problem in machine learning. Extrapolating away from your training region tends to be a failure a lot of the time. So we gave up for a while. Thought we couldn't do this. Then my student had nothing better to do, was looking through the CS literature, thank goodness, and he discovered this paper from 2.5 years ago by these folks, implementing something called the equation learner neural network. Maybe you're familiar with this. Here the premise is, instead of using, throw away that notion this is a neural network. Get rid of the activation function, ReLU, Tanch, whatever. Stick in a function that is meaningful for your problem. So that might mean if you know that the problem is a pendulum oscillating, stick in cosine for your activation function, right? Because cosine is going to be part of the solution. That was the original motivation of the paper. For us, what we're going to do is we're going to take quadratic products. Okay, so sometimes we're going to feed from one layer to another directly with a standard method, and other times we're going to take products. All right. So, so here are the details of the neural net that we used. How does it do? All right. So this is the training set that we're going to use. Okay. So when we extrapolate, we're doing pretty well. Right. So which is good. More importantly, this was the old results where we're consistently underpredicting the number of triangulations. Now the errors are well distributed around 0, so that gives us hope. And then we let it rip. And what do we get? So we get this number, 10 to the 10,505. We now know that, of course, that's an overcount, of course, by many orders of magnitude. But nevertheless, this thing did a pretty good job. Now we have some reason to think, thanks to Liam's talk, that this was good. But how do we test it? Let's go down one dimension. Let's do the 3D reflexive polytopes who have 2D faces and see how we do. And we did pretty well. Right, so the blue is the correct, blue is the predicted and red is what's known. Right, so out here is the one we don't have any knowledge of, but we predict. That's the 491 case if you want to think about it in the 4-dimensional case, but in the 3D case, we do pretty well. This worked. I have no idea why. So that's my questions to you. So the problem I just showed you in 5 minutes is essentially a canonical problem in string theory. We don't even have a representative sample of the thing we want to know. And furthermore, we're going to need to extrapolate from what we can calculate to some extreme regime where we can't calculate. These are the problems we need to address in string theory. For those of you who are machine learning experts, I'd like to know, this is basically a regression, right? If you look at what we get out of this thing, it's a regression. So why couldn't I have just done something like polynomial features on and done a regression and got the same result? It doesn't work. I really don't know why. What is the magic secret sauce of this? I don't know. Hopefully you can tell me after the break. Thanks.
All right. Thank you very much.
I have a question for the first speaker, Yan Hu. Basically, there is a known mathematical methodology for computing topological invariants. It's called spectral sequences. If you have filtration, it looks somewhat like a neural net, right? Except it is preconceived, not trained. Was the topology of your neural net anything like a spectral sequence would have been?
Not that I know of. In fact, that's exactly the technique that we used to do to compute this topology, especially for elliptic vibrations. We would just chase those sequences until we're blue in the face. And then you find that at least some of this has been implemented, say, by Macaulay or Singular or Sage, and then that does a bit better. But very, very quickly, as the degree of polynomial gets higher or the number of variables get higher, the computer can't do anything. So the neural net for the Hodge number I tried, that was just a total random guess. I didn't even optimize on the architecture. Just some combinations of hyperbolic tangents and sigmoids. So it could be you could find better ones for sure. But that's actually an interesting point to see whether structurally you could let the sequences inspire what kind of architecture you use. That's
so neural nets are believed to learn some high-level features, right? And this is what spectral sequence does in a sense as well. So yeah. there is a expected analogy there. Would be interesting.
It would be. Yeah, that's a good point.
Hi. So for Cody, so for your data, was it? So were you essentially testing on the training set, or was it a separate test set? The graph you showed.
Yeah. So the data we had with this was H11 equals 15 Calabi-Yau data, and so what the game we were playing was we were allowing these random walkers to go through and find different sigmas, right? Find different standard deviations, and then we would compare these, right? We would draw some number of draws, and then we would compare them using something inspired by Kullback-Leibler to compare these distributions.
So it was just an optimization problem. There's no generalization per se.
No, it's not tested on train set.
I see. And sorry for Brent. So the regression problem was it? So it was literally just a 1D problem, like 1D to 1D. Is that correct?
No, but I mean, so part of the reason this thing is called the equation learner is that the idea is that it's going to output something that's supposed to be meaningful. So we actually took a look at how it takes the 21 inputs, creates a polynomial out of them, quadratic, and generates our output. But we couldn't get any rhyme or reason out of it. So I wouldn't say it's a one-dimensional problem. I mean, I'm predicting one quantity, the log of the number of triangulations, but I've got 21 inputs.
I see.
But when if I preemptively take quadratic products of all the inputs and then just do a standard supervised learning, logarithmic regression or whatever, I don't get a result that works. So.
Okay, maybe two more quick questions, but we have to move on, and then we can discuss maybe later in private.
For the first speaker, when you're thinking about using machine learning to replace things that are typically done with Grosvenor basis like algorithms, what are you thinking exactly? Namely, I could have a set of polynomials in 1 variables, in 100 variables, and maybe I want to find irreducible or factorization. What would be the input to the neural network, and what would be the output? What is it that you're thinking?
Yeah, so for some of the varieties that we put in, the inputs would just be multi-degree in, for example, multi-degrees in products of projective spaces. So it's just an integer matrix. And if you're doing the kind of thing that these guys are doing, it'll be just the polytope data, which is also you can always kind of massage your input variety into some kind of a matrix or tensor of integers.
Okay. One last quick question. Sorry, can you ask your question?
So it's also for the first speaker. So I wanted to ask, since you are predicting Betty numbers or Hodge numbers, they are not just numbers. So the errors in topology transform the whole numbers in a certain way. So I was wondering if you actually measured your distance and your error in a way that is topologically meaningful.
Oh, that's a good suggestion. So what do you mean? You mean by varying the...
if I break a void, I get... basically, if I make an error in one Betty number, I break a void, I can get something like a lower dimensional topology. So I would get an extra error in another dimension.
A topology change, right? Yeah.
Yes, and that would be kind of the natural thing to say, that you are, if not exactly the correct topology, you are in a neighborhood in some sense.
Right. That's a good point.
All right, I'm sorry, we have to move on. So let's thank these 3 guys again. Thank you. All right, we continue with Sergei Gukov.
All right, I'd like to start by thanking the organizers for bringing me here. This was exceptionally inspiring and refreshing, so thank you very much. Also, thanks a lot to several people, some of them not included here, from whom I learned a lot over the past year or so, and with whom we discussed some of the ideas that I'll present to you. But I'd like to start with a general question of how machine learning can be helpful for either physics or more generally even mathematics by finding the killer application. So that's what we really need in order to convince hard-boiled skeptics in science to accept machine learning as a very useful tool for physics and math. It hasn't happened yet, and the question is, where could it come from? So where would this killer application be? The great opportunity actually presents itself since scientists, the way they work, is what psychologists would call confirmation bias or anchoring. So they're subject to this kind of frameworks where we find something, and then everything else we discover, we're trying to feed into this framework. That's where anchoring is. And machine learning can help us to find a new pattern, new sequence, or new relation that has not been predicted or doesn't simply fit in this framework. So that's where we could break this tunnel vision of traditional science approaches. And what I want to present to you is a particular area of physics and math. It belongs to both, where I think great opportunities for such new patterns belong. So this area is, in mathematics, would be knot theory, but it's also area of physics because questions I'm going to pose are equivalently questions of topological quantum field theory or topological string theory, very similar to the ones that were presented. So a knot is a knotted loop like this, and question is, are these two the same? So can you guess? Can I see show of hands who thinks they are the same? Nobody thinks they're the same. Who thinks they're different? Okay, many more people think they're different, but they're actually the same. So, and of course, we have to clarify what we mean by the same. The color is different, but that's not what we really care about. We care about topology. So every time I ask this kind of question, I think about this cartoon. So we're trying to distinguish something that's hard to distinguish. A more elaborate version of this question would involve these two guys, which differ only by one element. So in your data set, you're trying to do some mutation, and a question is, what about these guys? Are they different or the same? So in this case, they're actually different. So if you were voting on this one, you would actually be right. So our data set consists of such pictures, and of course, the way we want to feed this in a machine is not in terms of pictures. Luckily, this is perfect for machine learning in the sense that all this graphical data or knottedness can be encoded in a sequence of words in what's called braid group. So it's very algorithmic, and it's perfect for feeding into computer. So there are some equivalences on this data, which is quite interesting. So our data set is not just sequence of such words in a braid group or this kind of pictures. They're pictures up to equivalences. And equivalences are funny. They're not just rotations of a famous painting by 90 degrees. These are some moves which are very non-trivial elements in this braid group. So we are dealing with what yesterday we discussed at length, symmetries in machine learning. So these are symmetries on a data set, and our data points are actually equivalence classes of these objects up to symmetries. So the goal is to convert the data of these pictures, in this case knots, into some invariants which would be useful in math and physics. And some pioneering steps along these lines were done by Marcuse, who has a beautiful paper from a few years ago where he studied some simple invariants, or actually interesting invariants of knots, and machine tried to predict this invariance based on some relatively small training set. So it did extremely well, but then, this is particular knot invariant called slice genus, and this is the standard deviation. So you see that errors are pretty small, except in some cases they go from fewer percent and less to something like 0.3. So these outliers are actually exactly this kind of mutation-related guys, which are quite difficult, and especially difficult for machine learning. So I want to go to a class of applications that we're exploring right now that is much more rich, much richer than those simple invariants. And here the idea would be, or idea predicted from physics, is that every knot should correspond to some quiver, which is directed graph. And this would be, so this is called knot quiver correspondence. It's a very powerful duality which allows to encode a lot of useful knot invariants, very fancy ones like Hovanov homology, hyperbolic volume, you name it, in terms of this quiver data. So quiver itself also is very combinatorial, very algorithmic, and it would be interesting to program machine to actually find this correspondence. That's what we're trying to study right now. So thank you.
Thank you very much. Next up is Wardy Taylor.
Great, thanks very much. Well, I'd want to follow the other speakers in thanking the organizers for putting together this very nice meeting. It's a great treat to have this interaction between the two fields. I've been enjoying talking with a bunch of you all from the machine learning community. So I'm going to really just focus on a basic question, which I think underlies a lot of what those of us coming from the physics side here at this meeting are concerned about thinking about, which is to what extent can machine learning really give us some new, as people, theoretical insights into physics or mathematics. It's certainly clear that machine learning is good at a certain class of problems, classification, given lots of examples from certain categories. One way in which I've heard this distinction between the kind of questions I'm asking about here and these kinds of questions that machine learning is demonstrably good at is the difference between problems that humans can solve fairly readily by just looking at them. I mean, you look at that and you don't have to think about it. What number is that? And problems where a human has to reflect for a while or think for a bit about putting together an answer to the question. And so it's that second category I want to focus on. And really the question is, to what extent can machine learning learn or even teach us about new ideas? Can we give it data so that it will extract out some underlying equation or make a hypothesis about a pattern that we can then verify independently? Or can it prove new theorems, postulate new laws of physics? Lots of people here and this morning are talking about examples of efforts in this direction, but I think as Sergey just said, we don't really have a killer app yet, and we're sort of searching for that. And I think that's really our question. Again, to what extent can machines help us not only to reproduce the things we know we can do quickly as humans, but to understand and see new things currently outside our domain of knowledge. Now, this may seem a bit outside the realm of what you would think machine learning could do, but actually to me, AlphaGo 0 was kind of the real eye-opener, that it was able to do things that to me look like they fit in this latter category. A key example is finding a new Joseki or opening move. This is really a demonstrable thing. It's not just a machine being good at a game, but it's actually come up with a specific move. It's saying, okay, early in the game, when the corner looks like this, playing this is better than anything that any human has ever done. And that may be right or it may be wrong. We don't know how to completely solve Go, so we don't know. But it's certainly testable by experts playing it in games and seeing whether it does better than the traditional moves. So this suggests to me that there is a near-term framework in which machines may be able to come up with new ideas that expand our own abilities. So I'm going to give you a specific example of a kind of a math physics problem which does not have a known answer. This fits very much into the paradigms of what Mike Douglas talked about yesterday, and actually Liam's talk also. Sorry, Liam, I didn't put you up because I hadn't heard your talk yet when I submitted these. But here's the question. As Liam described, a Calabi-Yau threefold is characterized by certain data, and there's a theorem by Wall which says that if we know the cubic intersection form, which is a cubic form on the elements of the H11, and a few characteristic classes, that fixes the diffeomorphism type of a six manifold. So the question is, for what values of this set of combinatorial data, finite set of numbers, do you have a Calabi-Yau manifold, a Calabi-Yau threefold? No one knows the answer to that question. There is no mathematics that will tell us that a given set of those integers does not give us a Calabi-Yau threefold. On the other hand, we have this beautiful data set of 400 million examples. This is, by any reasonable definition, fairly large data. What can machine learning say about that? Could machine learning give us some insight into which sets of combinatorial data do or do not characterize a Calabi-Yau? Just to simplify the problem a little, here's a simple subclass of that. People have mentioned a little bit these elliptic fibrations. So last week, some work with my student Yu-Qian Huang gave us finally the number out of the 400 million that do not have a phase where they admit an elliptic fibration. It's like 29,228 do not. So, sorry, there's an extra 9 there. It should be 99.99% are elliptic. What that means is that for some d, the cubic form vanishes. So this is basically saying that this cubic form vanishes for a vector of integers. Could a machine have recognized that pattern? There's a nice recent paper by Yang Hui and Li looking at this from the point of view of the CCs. And Yang and I have been talking to the last couple of days about whether you could do this from this other representation that we use, which is different from the triple intersection numbers. But this is a hard problem. There's no algorithmic method, for example, known to show whether there exists a solution to a cubic Diophantine equation. So it looks like maybe this might be outside the feasible scope without a new insight, but maybe not. This problem that I just outlined seems to combine at least three very hard challenges. One is the problem of learning how to classify an object in a category without counterexamples. This is something people have worked on in machine learning, but I think it's still a developing area. Second one is understanding what machine learning systems are doing, interpreting. We've talked about that at this workshop. And the third aspect is the number theoretic aspect of this problem, which, as in many of our little intersect discussions yesterday with different people in machine learning, everybody on the machine learning side seemed to agree that this looks very hard from the point of view of the kinds of standard machine learning problems we're talking about right now. So this may be a hard aspect, but let me actually counterbalance that briefly by saying that maybe one way to think about what we're doing here is that machine learning may be a very useful general way of identifying problems where there's a simpler solution than we might think. And I think what Sergey talked about with knots, there's going to be a nice talk this afternoon by Vishnu Jajala, giving a number of other talks this morning, talking about examples where you try machine learning, it works, and then we have to understand why. It's telling us something new about the physics. Great. Thanks.
Thank you very much, Wardy. Okay, next up is Yizhuang Wu. You?
Yeah, thanks very much for the organizers for giving me this chance. So basically, I'm going to talk about something about machine learning holography. So holographic duality basically is a correspondence originally proposed in the string theory context as ADS-CFT correspondence, which is a correspondence between a quantum field theory and a gravity theory in one higher dimension. So the goal of machine learning holography basically we hope is to establish this correspondence not by human but by machine. So this has to do with our how this problem can possibly be tractable by machine, there's an analogy of a quantum field theory and image data set, which I try to say, is that you can think of a quantum field configuration as a certain kind of image, and then a quantum field theory basically ascribe an action to each image, to each field configuration. That is like assigning a negative log likelihood to each image in your data set. So basically, if you consider this Euclidean space path integral of a quantum field theory, that's basically an ensemble of images. So to learn a quantum field theory using machine learning basically is try to do a feature learning of this image ensemble. And how can we learn that? There's a powerful tool that physicists has invented to deal with quantum field theory. That's renormalization group. And renormalization group the idea is basically you try to cross-grain your images step by step. And during this cross-graining, you are throwing away irrelevant degree of freedoms and keeping the most relevant degree of freedoms. So this is like doing a convolutional neural network. But during this process, you are losing information. So usually people think, we think that it's hard to inverse this renormalization procedure, so it doesn't really form a group. But suppose if the degree of freedom, the irrelevant degree of freedom you throw away are really irrelevant to you, then why do you care about them? You should think about them as random noises. So suppose we can supply these random noises back on each layer, back into this RG transformation and run the RG transformation the inverse way. Basically, we are able to generate field configurations. Of course, we generate ensemble of field configuration because of this random noise. And then this becomes a hierarchical generative model. So I'm trying to say that training a good way to do RG is equivalent of training a generative model that maps random noise to your field configuration. And of course, the objective is trying to the objective is trying to build trying to bring close the generative model description probability distribution to the target distribution, which is given by the quantum field theory action. So basically, we build up a neural network which has a hierarchical structure, and then we start from some random noise in the bulk, and those random noise will be interpreted as the bulk field, and then map it to the boundary. And then in this way, we train the two probability distribution as close as each other by minimizing the KL divergence. So in the end, we establish a duality between these two theories. So we are saying this Boltzmann weight and this generative network probability distribution, they're close to each other after training. That means these two partition functions are equivalent. So this partition function describes the quantum field theory or conformal field theory on the boundary, on the holographic boundary. This describes some very heavy field propagating in the neural network in the bulk with some, the background is determined by this generative model. So what can we use? After the training, how can we use it? We can basically map the boundary theory back into the bulk and try to measure the residual correlation between the bulk field. These bulk fields are like latent variables. So their residual correlation function in the bulk or mutual information in the bulk basically can be used to determine the distance between every two bulk field variables. So because we're thinking that these bulk fields are very heavy, so basically their correlation must decay exponentially. So in this way, you can, by measuring the mutual information between the bulk field variables, you can determine the distance between them. So if you can measure the distance between every 2 points in the bulk, basically you can back out the bulk geometry by measuring. So we basically measure the distance in the holographic dimension and also in the spatial dimension, and then we can verify that this geometry is very similar to this ADS geometry. So, thanks. These are my collaborators. Yeah.
Thank you very much. Are there questions?
I want to ask a question to the third speaker. How do you distinguish Lorentz signature and the Euclidean signature in the bulk?
Path integral.
But
Can you use the mic for the answer?
We're all doing it in a Euclidean way.
In the ADS ones, we can always do the weaker notation to distinguish the Lorentz signature and the Euclidean signature. How do you do that?
Yeah, it's the data is already in the Euclidean path integral.
Yeah, so could you do Lorentz signature?
No, currently,
okay.
not with this scheme.
But do you know anyway now?
Maybe we need to develop some dynamical. That you need a real-time dynamics.
So could we do that?
I don't know.
Okay.
I don't know a good machine learning framework to do that.
Thank you.
Yet.
Yeah, for the third speaker. Thanks. So my question is that how do you measure, you really approximate the distribution? You minimizing the Q divergence. Did you finally plot the Q divergence between your nerd distribution and the target distribution?
You mean loss function?
How small that Q divergence finally it will be?
How smooth?
How small?
How small?
Yeah.
I don't have the number, but I don't know whether it's the absolute number is meaningful, but you can think of KL divergence eventually as a free energy. You can calculate the free energy difference, and then the free energy per site actually is very small compared to the UV scale.
So essentially, my question is, how do you believe that you already learned the high-dimensional distribution?
Well, we have several checks. Like you can check the physics on the boundary. For example, we learned the CFT. You can check its scaling dimension. You can check its conformal dimension of the operators, and a lot of physics check you can do on the boundary to ensure that your generative model really generate the physics system.
I just wanted to comment very briefly that what you presented is very cool, and that in computer vision, the area of segmentation for a long time was based on constructing energies based on random fields. And so it's very related to what you were talking about. And today, of course, is done with deep learning and also with the integration of Markov random fields with deep learning.
I see. Thanks.
So let's talk. I mean, there's a lot of things that can be done.
All right. There seem to be no further questions, so we'll move on to the next batch of 3. All right, so we continue with Patrick Fautofange.
Okay, thank you, Fabian. First of all, I would like to thank the organizers for setting up this great workshop and giving me the opportunity to speak here. I'm presenting some work together with my PhD students, Andreas Mütter and Erik Paar. Erik Paar is also here in the audience. And the topic is seeking a connection between the string landscape and particle physics. So having a connection between the mathematical framework of string theory and particle physics using machine learning. Okay. Yes. So the framework that I'm doing here, after we have a very nice introduction by Liam and also by Mike, here in this talk, I'm going to a specific subset of the string landscape, the so-called heterotic string. And as we also already heard, string theory is conveniently defined in 10 space-time dimensions, which is depicted here by 5 orthogonal two-dimensional planes. And the aim is to connect this theory to the observable world, where the most striking difference is the number of spatial dimensions. We have to hide 6 spatial dimensions from observation. We have to make them small, so tiny that they evade the detection. This is what goes under the name of compactification. And in this framework here now, I have the 4 large dimensions of our space-time, and here the 6 tiny dimensions depicted by these pillow-like objects. They are called heterotic orbifolds. They are in a way similar to the Calabi-Yau's presented by Liam, but they are singular limits of smooth Calabi-Yau's, and string theory can perfectly deal with them. As Keith was pointing out, this is a CFT construction of string theory, so really like at the heart of string theory, but we are sitting at a small corner of string theory. In this corner of the string theory landscape, a string compactification is described by an order 100 parameters. So we have an order 100 dimensional parameter space. A cartoon should be this one. So each dot in this parameter space corresponds to a valid CFT string construction. And now from these parameters, we can compute the full particle physics model in 4 dimensions. And especially we can decide whether a model is a good model, that is, it is compatible with experiments, it describes the interactions that we know, it describes the particles that we know, or whether a given model is a bad model. for example, there wouldn't be nuclei or there wouldn't be electromagnetic interactions in a bad model. So we have to find the good models in this landscape. And the problem is that this landscape is huge. We are focusing on a small region of the landscape, so where the number of parameters here might be in the order of billions or a few orders higher, so much less than the numbers that Liam presented, but still the numbers are so big that it's difficult to just scan through all of them, especially because there's a huge symmetry group acting in this parameter space, which is related to rotations in 16 dimensions and translations in 16 dimensions. So we want to find the good models, and one way one could get all the good models is to find the inverse. I forgot to mention, we have a computer program, the so-called T++ orbifolder, which does the mapping between the models and the answer to good or bad models. And what we would like to have is kind of the inverse orbifolder. We want to find all the points in the parameter space which give rise to a good model, to a particle physics model that we can compare to experiments. And what we did in our work is to use an autoencoder to find conditions to find these good models in parameter space. Our autoencoder has this architecture. We start with an input layer of 962 dimensions. We use a so-called one-hot encoding of our parameters. In our case, it was 26 invariant parameters. And then we reduce the layers to the bottleneck of 2 dimensions, and then we have the decoder again. We train the network on a training set of like around 400,000 models, consistent string models, such that input and output agree. And then for each string model, we read out these 2 parameters and plot them as the coordinates in a 2-dimensional picture. And this is how the 2-dimensional picture looks like. So these are the first and the second latent dimension. Each point corresponds to a valid string construction. Most of them have nothing to do with the observable world. However, the red models, they are, loosely speaking, in agreement with observations. They are the so-called MSSM-like models. And even though the autoencoder did not know whether a model is a good model or a bad model, whether the model is blue or red, the autoencoder somehow clustered the good models on separated islands. And some of the islands I highlighted in green here. So somehow, even though the autoencoder was not trained whether a model is good or bad, we just highlighted it afterwards, the autoencoder could identify good models as being special in the landscape. Okay, thank you very much.
Thank you, Patrick. Next up is Alex Cole.
Okay. Hi, everyone. Plan of my talk is I'm going to talk about this technique called persistent homology, which allows us to see the shape of data, broadly speaking, and then I'm going to try to talk about 3 physics projects. So buckle up. So first, the shape of data. Data is often well described by models based on shape, which is good. When we learn about the shape of some data set, we feel like we understand it better, we can describe it more efficiently. In this talk, I'm going to talk about shape in terms of topology. So for us, this means clusters and n-dimensional holes. In the language of homology, these are non-trivial cycles. The easiest way to get intuition for this is to look at an example. So this is the Vietoris-Rips filtration. What we're going to do is introduce a scale. We draw balls of this scale and connect points that have overlapping balls with edges. And then if we have enough edges to fill in a triangle, we fill that triangle in. If we just chose one scale, we would be asking for trouble because that's not a very stable choice. So what we do is we vary the scale. So here we're increasing our coarse graining scale, and we have more edges, we fill in more triangles, and so on. We keep going. Eventually, we have this strong feature that you might have identified on the first slide. That's why we call this an annulus. And as you go even further, it just becomes a blob. So even that feature goes away. So what we just did is persistent homology in an example. What we look at is the persistence of topological features across different scales. It turns out that when you turn the crank, you can actually track individual features. And so features that we think of as important for the distribution of points will live far from this birth equals death line. So we do a scatter plot called a persistence diagram. for when various features are born and die. And if a feature is alive for a long time, we think of it as significant. A nice feature of this process is that under a natural metric, it's stable against perturbations to the input data. Another example of a kind of filtration is a sublevel filtration. So say you have some function on a domain. This could be an energy function or something. We look at sublevel sets and we increase the threshold. And we see that topology change for these sublevel sets is related to critical points of the potential. So this is familiar from Morse theory. I'm skipping this. This is what it looks like in a two-dimensional example when you increase the threshold. All right, 3 applications to physics. In the first, we actually use this sublevel filtration. So we look at some simulations of the cosmic microwave background. We have these temperature fluctuations, and the statistics of these can tell us a lot about the early universe. And so what we did is we performed sublevel filtrations on simulations for varying levels of something called primordial non-Gaussianity, which would be really great if we could find it because it would tell us a lot about inflation. So doing a toy likelihood analysis, we improved a certain class of observables by about a factor of 2. So these numbers are by themselves not that meaningful, but the important thing is that this number is smaller by almost a factor of 2. The second application is to the string landscape. So as we've heard a lot today, we have these big numbers. We have this huge data set, which is all these ground states of string theory. We would like to tackle this better. It looks like the figure didn't exactly show up. That's fine. So we feel like if we could understand the string landscape better by looking at structure, this would be a valuable thing to do. So it's unfortunate that this figure didn't show up because it's very beautiful and interesting. There are lots of voids in it, so you talk to me later and I'll show it to you, or look at this paper. So it's natural to try to characterize these kinds of data sets with persistent homology. So we're looking at the distribution of string vacua in moduli space once you've stabilized your moduli. Okay, the final application is to statistical physics. So we've been looking at how well persistent homology can distinguish between different phases of matter. So if you wanted to do this, the first model you would look at is the two-dimensional Ising model. So what we do is we take the spin sites that have the majority spin. So if most of the spins are up, we take those as vertices, and then we perform one of these length-based filtrations to look at the pattern. So in the Ising model, it's really easy to tell by eye the difference between these two phases. But it turns out that when you turn the persistent homology crank and do some logistic regression, you can recover magnetization as the order parameter. And also, if you do unsupervised learning, if you do a clustering on your persistence data, you can recover the temperature of the phase transition. And so we've also looked at this other model, this square ice model, and we're looking at more models now. It's kind of harder to tell the difference by eye between these two phases. And so the ground state is in this Coulomb phase, this frustrated phase, and we recover something that's kind of non-trivial and non-local, and we're working on it. Thanks.
Thank you, Alex. Okay, next up is Ms. Bowcock.
Great. Okay, over the next few minutes, I'm going to tell you a little bit about why we're interested in machine learning. I'm a particle physicist, an experimental particle physicist, not a theorist. I work at Liverpool, and we do experiments all around the world, and I'm going to concentrate essentially on the ones we do at CERN today, and one very specific one, that's the LHCb experiment. Our job is our first job is we actually provide the core of these detectors, which are these big 3D cameras. And that's at the heart of them. For machine learning, we actually partner with the Foundation Bruno Kessler, and now with Microsoft, and we're actually running a hackathon in Trento in 2019. Right, so the big problem we're trying to crack with machine learning is that there's a shortage of about an order of magnitude in what computer power we need to actually analyze the data that comes out of these machines, and we think machine learning is part of the solution. Right, so as I say, the exemplar is the LHCb experiment. It's, broadly speaking, the highest data throughput at CERN. It's key to looking for rare processes in the early universe, and the key problem is we take 40 million frames a second, and from those we have to reconstruct these so-called tracks that tell us about the high-energy particle interactions. So our strategy to try and crack this problem, first of all, we have to build the detectors. Fine, we've done that. They work beautifully. And then we actually try and get and we've written the code for them, and it all works great. We get the physics out of it. But then afterwards, we're trying to replace this with machine learning, because we hope that by replacing 100,000 lines of code with some machine learning and then putting it on an FPGA, we can get more performance. So we have a very simple a fully collected neural network, which we've actually shown can replace our 100,000 lines of code, essentially, and deliver tracks for us successfully. We've already shown, and we did so last year, that our efficiency versus purity of performance matches or exceeds the current algorithms, and this enables us to reconstruct the physics that we need to be able to do. So what we're about to do is we're going to try and extend what we're doing on the Azure FPGA platform using the Onyx format. And the key is eventually we want to attack the problem of replacing some of these 200,000 cores that we normally use to process the data actually with machine learning algorithms running on FPGAs. And to give you an idea about the amount of data that's flowing around this process is about 0.5 picobytes per second. So this is a real serious data flow problem. Right, so how far have we got? Well, as I say, we've shown the algorithms in principle work, but what we need to do to show this really works is to get Azure to work in production, piggybacking on the current existing system at CERN, and we're looking at doing that at about the 10% level, and we're already discussing how to build the prototype to do that this year. We will at the same time continue to build some of our machine learning algorithms, making them more detector agnostic, and then maybe even transfer them from CERN to some of our experiments at Fermilab. So this is a general problem across the field. So, very broadly, what we're trying to do, we're trying to crack this fundamental problem in my type of physics, that there isn't enough computer power. And what we've already shown is that we can crack the single biggest problem, which is tracking, at least in our experiment, and show that machine learning algorithms can actually deliver what is needed. And now we're in the business of offering an implementation which we can actually put onto FPGAs, and possibly even beyond that on different types of hardware. And I think one of the things that's very practical about this is something that we want to do this year, and of course then expand to other labs. So there we go. Very sweet, short story. You can ask me details about that later. Thank you.
Thank you very much.
Quick question for the last speaker. So one of the things about machine learning is it can have blind spots to things it wasn't trained on. So how confident are you that if there's some anomalous new physics that arrives in an event that is not in the data set you trained on, that you'll spot it?
Yeah, well, what we're doing is we're just replacing the tracking. We're not replacing the physics analysis. So the core of what we're doing is replacing what we call the tracking, which is sort of mapping the trajectory of these particles through the detector, which takes over 70% of our processing time, and then building the events. We're not, I mean, the question you're asking is a very sophisticated question about how I find new physics in a data set. That's not what we're trying to crack. We're trying to crack, if you like, the front-end problem.
Question for Alex. So on your condensed matter example, which parameters are you interested in mostly? Is it like, phase to detect which phase it is in, where the phase transition is, or what?
Yeah, so it would be nice to be able to find the phase transition temperature or something, or also if you have two different phases, if you have some kind of phase that's kind of complicated to describe, like a topological phase. Could you come up with some way to characterize it that is simpler?
And so there have been some efforts, obviously, doing these kind of things. Is there already a reason why you think TDA can, perform better, or how does it compare to existing methods?
So what kinds of techniques are you talking about?
Yeah, so there has recently a paper on using support vector machines to do this, and.
I think one nice thing about persistent homology is its interpretability. You calculate the diagram and you know that you have a loop, or depending on what you have, of some size, and you can go back and actually find it in your configuration. So that's one thing I like about persistent homology.
I have a question to the last speaker. So I heard that so you are using the tagging.
Sorry?
You are using the machine learning in tagging process. Is that true?
experiments are using the machine learning tagging process, and there's a representative of one of these experiments that's doing that in a big way. We also do it, but what we're talking about specifically here is and there's nothing wrong with that. That's very important. But the problem we're trying to crack here is the online problem and the fact that we can't process all our data the way we want to do it. How you offline manipulate some reduced set of code with very fancy machine learning algorithms is quite a different problem. This is a data throughput problem in real time where we're using the machine learning to really compress the amount of code and speed it up through the ability to do parallel processing. It's a different problem.
Okay, I see.
All right, I'd say we move on in the interest of time. So we thank the speakers again and move on to the next batch. Okay, so next up is Maria.
Hello, and thanks for being invited to this workshop. Thanks to the organizers. This talk will not have any algebraic geometry, so it will have no algebraic geometry and no topology. It's going to be about manifold learning. But I want to say that topological data analysis is on the horizon, and we have not started doing it, but my group or somebody else should actually start doing it. So I will start with a 10 seconds advertisement. This is a program that I am co-organizing at IPAM this fall, and please take note and maybe participate. Another advertisement is that because I'm going to talk about manifold learning, it is important. Manifold learning is data hungry, and we'd better have the capacity to process large data sets, and now we have it. And so I saw that some of you are familiar with sklearn. The interface of this package is practically copied from sklearn, but what is underneath is much more computationally efficient and also implements the state of the art in manifold learning, like the theoretical papers. Now, what I want to talk about today is about dimension reduction, and dimension reduction as a tool for scientists. And in some sense, my talk is in spirit very close to what Washington Taylor talked about, but in practice, it's a very different domain. So scientists have try to find simple laws of physics, try to describe complex phenomena by smaller number of parameters, and dimension reduction, linear or nonlinear, is in some sense the mathematical tool or the algorithmic tool to do this. And as a motivating example, I have data from molecular dynamic simulations. So this is all computer-generated data by better or worse models of physics. So these are data that we sort of understand or should be able to understand the moment we have generated it. But in some sense we can. We compute averages of whatever quantities we want. But in some sense we cannot understand things about the shape of the data. And therefore, manifold learning performs this function for us, creates something which is a two-dimensional manifold, which happens to have a, let's say, torus topology in this case, which we look at and we say, yes, we understand. Now we see what's happening. But this is not completely true. We only see what's happening for a small molecule that we already understand. So if we want to actually use manifold learning to help scientists, we have to, I as machine learning want to do more. For example, it is known that these algorithms, actually it's a good point. How many of you have used manifold learning algorithms? All right, so these are actually algorithms that agnostically take data like this and map it into low dimensions in a continuous way. It is very well known that they distort the data. So is this the shape of the data or not? And I will show that this is not the shape of the data. But more importantly, what's the meaning of these coordinates? If you have not used manifold learning, I'm sure you have used Carhoon and Love. And essentially, these methods give you what amounts to abstract coordinates. And then people visualize, basically color the manifold, and I colored it with the rotation of this metal group with respect to the molecule to actually visualize what the coordinate means. And by that, they discovered that this first coordinate is the rotation of one group in the molecule. Well, if we want to do science with machine learning, we need to actually answer these questions automatically. Visualization for data that is more than two-dimensional doesn't help. And the artifacts actually can confuse. So what I would like as a program is to create algorithms that remove artifacts, create new are quantitative in the sense that visualization is qualitative, and visualization asks the physicist to actually check whether the algorithm did the correct work. I would like the machine learning to do the checking and offer the physicist some guarantee, a quantitative guarantee. Moreover, I'll talk about what the meaning of the coordinates is. Abstract coordinates do not transfer well. Science wants to transfer knowledge. Abstract coordinates are transferred only after somebody explains them. So I would like to do that automatically. So I will spend 1 minute. All right, so I will skip the distortion. I will say that it can be measured if you use Riemannian geometry, and it can be also corrected. So this triangle was an artifact. The true shape is a circle. And I will talk about the meaning of the coordinates. So the ethanol molecule has two groups that can rotate relative to the rest of the molecule. And we can see that this torus is actually parameterized by these rotations. Can we discover this automatically? And my answer is yes. And I have only 30 seconds. So what I want to say is that what I want to do is ask the physicist to give me a set of functions that are interesting. In particular, this could be all the rotations in a molecule. And from these, I want to automatically choose a small set that parameterizes the molecule. But this should be parameterized in a way via a nonlinear arbitrary function. And it has to be an arbitrary function because every manifold learning algorithm gives me another parameterization of the manifold. So a diffeomorphism of this manifold is still a good embedding. So I cannot put any constraints on this function, except that it's smooth. And the idea is to show that basically if you go to the differentials, then nonlinear function composition becomes linear regression. And this is a tool we use. And in the last seconds, I'm going to show that actually the particular linear regression that we set up does identify among a set of torsions the ones that actually represent parameterize this manifold. Thank you.
Thank you very much.
Hello. Hello.
Next up is Yichen Huang.
Yeah, my name is Yichen Huang, and I'm presently an AI resident at Microsoft. I don't have any slides. And my 5-minute talk will be an introduction to applications of machine learning in quantum many-body physics. And before I come into Microsoft, my background was in quantum many-body physics. There are at least two major directions of using machine learning techniques to study quantum many-body physics. Here, major means that there are a lot of papers in each of the directions. The first one is about classifying phases using methods in machine learning. In order to use machine learning, one needs to have some data, and the first question about classifying quantum phases is how to generate data. And the basic approach is just to perform a Monte Carlo simulation, and we have many samples, and then we can try to find out the patterns in these samples that tells you which phase the system is in. And after you have gathered data, then you can directly use machine learning methods, either supervised or unsupervised. For the supervised case, you need to train a classifier, and for the unsupervised case, one can directly use some basic techniques like PCA or clustering. But one interesting question regarding this line of research is that, for instance, if you already can perform a Monte Carlo simulation, then why not directly compute the order parameter rather than using a machine learning approach? There are more than one answers to this. First is that if, for instance, you do not have usually we need to solve a problem which is new in the sense that you do not have an understanding of good understanding of the system. In this case, you might not know what order parameter to compute. In this case, machine learning, in some sense, automatically helps you to find out the relevant patterns in your data. And the second is that even if you already know what quantities to what order parameter like correlation functions to compute, then sometimes Monte Carlo simulations can be very slow. The convergence can be very slow, but if you use machine learning, then it might be possible that the machine learning can help you to find out some hidden patterns in your data which are sufficient for telling you which phase you are in before the convergence of the computation of order parameters. And in this way, it might be possible that machine learning can help you reduce the number of samples that you need to generate. The second direction I would like to mention is about the simulation of quantum many-body systems using classical computer with neural networks. And the idea is quite simple. That is, we try to build a representation of the suppose you need to, for instance, find the ground state. You can just build a representation that is parameterize the wave function by neural networks. And then if you would like to compute the ground state, you only need to minimize the energy with respect to parameters in the neural network. And in this case, one can just use standard optimization methods like gradient descent. Initially, people are using very simple architectures like one-layer neural network, and in this, if you use this architecture, it is sufficient for some simple models like 1D quantum Ising model or Heisenberg model in 2 dimensions. But if you would like to work on more challenging models. Here, challenging means that it is difficult for traditional methods in quantum many-body physics. And if, for instance, a 2D G1, G2 model, then it is necessary to use more complicated complicated architectures like deep convolutional neural network. And in this case, the best known result for machine learning, for neural network methods is nowadays is comparable to the best results using traditional methods in quantum many-body physics. And it is interesting to see whether one can improve the neural network methods to gain some insights beyond state of the art.
Thank you very much. All right, and our last speaker is Vishnu Jejana.
So I'd like to begin by thanking the organizers for the opportunity to speak here. My work is in collaboration with Arjun Kar, who's in the audience, and with Ankar Parikar at Penn. So like Sergey, I'll be discussing some physics of knots. So knots are S1s embedded in S3, and there are some various examples of knots that I've drawn. Related to these knots are several invariant quantities. One such invariant quantity is a Jones polynomial. For example, for this figure 8 knot, I've written down this Jones polynomial here. And another such invariant quantity we can associate these knots is a hyperbolic volume. We essentially subtract the knot from S3, and we compute this volume using a tetrahedral decomposition. This hyperbolic volume applies to a certain class of knots that are called hyperbolic. All knots, according to the theorem of Thurston, are either elliptic either torus knots, hyperbolic knots, or satellite knots. At a given number of crossings, most knots will be hyperbolic. In addition to the Jones polynomial, we can construct more refined invariants. The colored Jones polynomial, we attach an extra index n. And Sergey and others have constructed a conjecture that says that in the limit where n goes to infinity, the colored Jones polynomial encodes the volume. So what I'd like to do is try to see whether we can associate the actual Jones polynomial by itself to the volume. A more refined invariant is in Kovanov homology. And Dunfield and Kovanov noticed that certain quantities, like the Jones polynomial evaluated at -1, or the rank of this homology, are related to the volume. In addition, there is a volumish theorem that relates coefficients in this Jones polynomial as giving upper and lower bounds to the volumes of knots. if we apply this volume-ish theorem by just selecting points within this range, we find that the actual value of the volume is relatively poorly described by choosing a point within this range. If we apply the Kovanov rank to encoding the volume, we find that it's a reasonably good fit, but there's a 4.67% error in using this rank to predict the volume. So let's use a neural network. We just train with various values of the Jones polynomial, and we get we tell it the volume, and we ask to see how it performs on unseen data. So we train with a 2-layer neural network with 100 neurons per layer, and we use logistic sigmoids. And we find that with training with just 10% of 313,000 knots up to 15 crossings, we get 2.45% error in assessing the volume based on inputting the Jones polynomial. This is already, even with a very, very tiny fraction of the data, this already outperforms the Kovanov result. So just training with 313 knots out of this huge number, we get a better percentage than we saw with Kovanov homology. So as Wadi mentioned in his talk, we like to see whether we can get exact results or use machine learning to motivate us to find more rigorous results analytically. So we're seeing that the volume is some function of the Jones polynomial plus small corrections. There's small corrections here because given a Jones polynomial, different knots with the same Jones polynomial can have different volumes. So the spread in the volumes for a given Jones polynomial as replicated in this data set is not very large. So we're learning this f of j pretty well as giving us most of the result that we're looking at. We can also notice that there are failed experiments we can attempt. So we've used the Jones polynomial to try to learn the Chern-Simons invariant. We don't do very well, whereas we do pretty well with the volume. So maybe these failed experiments can teach us something about what the results might be for the form of these analytic functions. We've also noticed in various examples of Clabials and with bundle cohomology, for example, the existence of underlying homology or cohomology structure is a diagnostic for problems that are machine learnable. Maybe that's the same case here with the knot invariants. So ultimately, I'd like to find some knot machine learning result, and we're using these machine learning techniques to motivate us in this direction. So thank you very much.
Thank you very much. Are there questions?
A question for Marina. So in terms of manifold learning, if I'm interested in the learning in the embedding metric, where are the bottlenecks in some sense? So like if I look at many parameters, like how far can you push many parameters, and also situations where you have multiple scales involved, and it's like that.
Is this working? So I will try to answer like this. Multiple scales. So it depends if, does it work now? It depends if you ask a theory. So the theory for multiple scales, as far as I know, is not developed. But we have a data-driven method that currently, also asymptotic theory says that single kernel, single scales should suffice because the density is almost uniform in all the theorems that exist. But as we see, the density is not almost uniform in real data that we care about. So I think the theory must be improved, but before the theory is improved, we have a data-driven method that can estimate smoothly varying bandwidths and scales too. By the same method. Right now we use the constant one, but we can use that. The question about other bottlenecks, I'm not sure I understood. Like how many dimensions can we handle, or how many ambient dimensions can we handle? So how large intrinsic dimension or how large ambient dimension?
Intrinsic. So in the end, can you have something with 100 parameters, for example?
The statistical answer is no, because the sample size has to grow exponentially in the dimension.
Further questions?
I guess this is a question for the last speaker. Computing Kavanagh homology is at least exponential, and Jones polynomial is known to be exponential time. Will these machine learning algorithms make it faster to estimate the Jones polynomial, for example, if you knew the volume?
We're trying to do this exactly. We're trying to do the inverse problem and start with the volume and train on Jones polynomials and see whether we can do the same thing in reverse. I don't have results to report, but we can certainly do this in an attempt to see what happens.
Okay, there doesn't seem to be there are further questions, so we thank all the speakers again.
So next up, we're going to have panel sessions, actually one panel session, and we're going to have 6 eminent participants of our workshop up here. Sorry, not 5 plus 2 of us, showrunners, but it's not going to be just a panel discussion. It's going to be an audience plus panel discussion with the limelight on the panelists, the eye candies. But the discussion I hope to have between everybody in the room. So panelists, please come up right now. So why don't we go from right to left and have everyone introduce themselves very briefly.
Well, I first want to thank Greg and the other organizers for putting together a great meeting, and all the people who spoke, really interesting talks. I learned a lot. When I listen to these talks, I tend to exercise a filter of some kind, to try to see, where my previous work or knowledge, might be relevant. And one of my filters is smooth topology, and that one didn't work so well during these talks. It seems like the landscape is very number theoretic and bouncy. And it seemed one of the things I learned is that when you go from layer to layer in convolutional nets, you're changing representations. I don't see how to do that smoothly. So one has to be flexible and be willing to throw your filters in the trash. That's how you learn. So that was a good exercise. Another filter I often use is quantum computation. And of course, we don't have quantum computers, and this is a practical subject. But listening to the rate of progress in string theory, I'm not overly concerned. I think we have another decade to develop quantum computers in order to contribute to this problem. Closer to my mouth? Okay, yeah, thanks.
Is it on?
Louder. Oh, was it off?
No, try again.
Oh, hello, is that better? I'll just speak up.
Hello?
Hello, does that work well? Yes. Oh, okay, good. Okay, all you missed was my joke about progress in string theory being a little slow. And I think we have time to develop quantum computers to help. And some evidence that this might be interesting came from this phrase I heard in one of the morning lectures, Platonic dataset, which I really liked, because quantum computers are very fast in principle once we build them, and algorithms take often like log squared time or something like that, like the factoring algorithm. But if you have linear time to load data, it's no advantage to be running in log squared time. So one always worries about the applicability of quantum computers to data-intensive problems. But if the data is, for instance, number theoretic in nature and can be generated in superposition, that problem disappears. So I really like the idea of applying neural networks to Platonic sets, and eventually maybe we'll apply quantum neural nets to Platonic data sets. When thinking about...
Sorry, Mike, this is just an introduction.
Oh, well, I was... Oh.
I want to get everybody to have a chance.
Okay.
And then we can go into more in-depth discussion. Sorry about that.
Sorry.
Okay. So I'll do a little introduction. So I'm Washington Taylor, Waddy for short, at MIT. I might have mentioned to some of you, I thought about neural networks a bit 30 years ago before I went into physics. I worked for this company, Thinking Machines, studied AI at Stanford and was very excited about it, and then decided this was just too hard a problem. So I went on to quantum gravity for the last 30 years. And now I'm really excited to see all the progress that's been made. So just to briefly comment on one of the things that Michael said, I actually think the progress in string theory has been incredibly rapid. The issue is just that we're going a very far distance. So we're moving very fast, but even at sea, 100 light years is a long ways away. So
that's what I tell my manager.
Right. So we're working on hard problems. Anyway, so I just very briefly, my own excitement about the potential relevance of neural networks in our field has been really going up and down on an almost hourly timescale at this meeting. I really have enjoyed the talks and this intersect, and I think just as I was saying in my brief talk this morning, I think maybe one of the big opportunities is that we really don't know which problems in string theory neural networks can apply to, or even what the right methodology is from the mathematical point of view for some of them. So actually playing with neural networks as a way of seeing which problems may have a simpler solution than we think they do seems like a very promising thing to me. The last talk by Vishnu was a great example of that, I think.
Yes, I'm Paul Smolenski. I'm part-time at Johns Hopkins University and part-time right here at Microsoft Research AI. I started in physics and decided that problem was too hard and switched to artificial intelligence. So my transition occurred in the early 80s, so physics was different, and so was artificial intelligence. But I was part of the previous generation's seminal group, if I can use that phrase, for the group at UC San Diego that in cognitive science brought neural networks to the fore as a way of trying to understand cognition. And my connection to physics is that in physics we have facility with working at multiple scales and seeing how laws change across scales. And that was a basis for trying to reconcile what in those days was a large battle between those who thought that the secret of intelligence had something to do with the architecture of the brain versus those who thought it had everything to do with logic and grammars and rule-based systems. So for me, the idea was that these are both informative formalisms, but at different levels of description or different scales. And so the methods for bridging those two that I have used come out of physics and have shown that these connections can inform how to do work at both levels from taking insights from the other. So that's a different use of physics than most people have been talking about here.
I work in probability, mathematical physics, kind of lattice models, conformal field theory, and now neural networks. Yeah. Okay.
Yeah, this conference has been wonderful so far. Okay. So, what can I say? So, how did I end up working on this? I mean, I think the common feature between, say, objects like the Ising models or lattice models or conformal field theories and neural networks are just that they are objects I find beautiful, and you can play with them, you can somehow simulate them, you can look at them as they evolve, and you can already tell without having a mathematical result that there is something to be discovered. My goal is to uncover objects that are relevant to describe things that you can already see with your eyes look non-trivial. So okay. So that's what I do, yes, so far it's worked somehow for both kind of questions. I mean, I think one of the general things that I find very powerful, and it's not always emphasized, is you really need to find. It's much easier to find a lot of linear problems to solve, millions of linear problems than to solve a nonlinear problem, and often that's been, a kind of common feature in what I've been doing, is to try to solve many easy problems at the same time. Is actually much easier than solving one hard problem, and it allows you to go a bit further. Okay.
All right. So I'm Gary Hsu. I'm from the University of Wisconsin. I'm a physicist working on string theory and cosmology. I'm one of the organizers, and I should say that I'm a last-minute replacement of an eye candy who is too shy to come up. So I'm excited about this meeting mostly because I wanted to learn about what can be done about solving hard problems in string theory, and in particular, whether the flow of information can go in both directions, not only applying machine learning techniques to solve problems, but maybe some of the physics ideas can inspire methods in machine learning. And I'm happy to see that, in the talks that we have heard in the past 2 days, there have been interactions going both ways. So.
Thanks, everybody, for your introduction. So I guess my first question for everybody here, the audience and the eye candies, is, in what ways has physics and ML intersected so far? What are your favorite ways in which it has intersected? And what do you think are the open questions that we should take away from this intersection going forward? What are the most exciting problems, insights that we have seen so far in these events that we should take home? Anybody? On the panel?
I mean, one thing that we heard about just a few minutes ago from one speaker, but we didn't hear too much about here, is the role of machine learning in experimental physics. And I think machine learning has actually already played a vast role in experimental physics at the level of tracking and also event identification and all kinds of things. That it has become a key component of the experimental physics enterprise. It's a little more closely tied, actually, to some of what the people here were talking about more directly related to image recognition and those sorts of things. But I think one of the big challenges is how much further can it go heading into the more theoretical domain. But that's just a direct answer to your question of where it's hit the most in physics. I think that's maybe one part of that answer.
My name's Gordon Watts. I'm an experimental physicist from the University of Washington here in Seattle. So this question and your comment really made me think about a division. So my background with machine learning has been using machine learning as a tool. And I use it to extract tracks, to look for bead tagging, to look for certain types of patterns in the detector. But we don't really use it very much to actually do the physics. Once we've got the tools, we build the building blocks, and then we do physics in a much more traditional way. Traditional meaning what we've done for the last 30 years. Listening to the talks this afternoon, I hear for some of the superstring work, it's the string theory work, it's very much similar in some cases where they're being used as tools to explore large parameter spaces. But there were also a couple of talks where it looked like it was making its way into the actual physics. And I would love to hear more about people's thoughts about how we're going to cross that boundary in the future, because that feels to me like it's a bit more of a frontier than, using things as tools and using it as tools in pattern recognition.
My name is Peter Bram. I work in computer science and mathematics, and I wanted to mention that in some of my interactions with people in the Flatirons Institute in a group for computational astrophysics, they stumbled on very different applications of machine learning to physics than we've discussed here. And a good example is that they used machine learning techniques to assist in solving differential equations, often not a complete solver, but something very close to a solver. For example, an adjustment to a simple solver with machine learning has been very, very effective for predicting early stage cosmological structures. I just wanted to bring this up because it shows, I think, that there is very, very much breadth to the application of machine learning. And here I think we've seen more applications in the direction of classification perhaps than in this kind of different things.
So this is like also on the replying to Gordon and kind of putting it to Paul Smolensky as a question, because like there seem to have been development in the machine learning community where something more theoretical versus something applied was already happening when you're talking about grammar and so on. Can you see any analogy in terms of physics to look at new models and, you know, to kind of bridge to this like we have a very analytic way of talking about the problem, which seems to be very relevant to one side, but we also have a, I mean, numerical side as well to it. Yeah, can you see some similarities in this?
Well, that's a good question. So I guess in certain communities within cognitive science, including people working on language, there is some interest in viewing not just an underlying neural network level substrate as a dynamical system, but also viewing more high-level cognitive systems as continuous time dynamical systems. And that's certainly a potentially big break from how processes at the high level have been thought about in the past. So aspects of classical physics can inform new ways of explaining how the computations that we do in terms of the actual level of the functions we're carrying out can be done. As far as the string theory connection, I have been struggling with that while here to see whether there's any potential connection to aspects of cognition that I know about that might be informed by findings and methods from string theory. But I've yet to come up with a good case for that. So I'm still thinking about that. Thank you for the question.
I'm Akio from Brookhaven National Lab and New York State. I'm working on theoretical physics, especially lattice quantum chromodynamics, by using supercomputers. And I really enjoyed this workshop, and how to say, I found that there are several similarities between the machine learning and physics. And I know that there are some example about like the Boltzmann machine. It's nothing but the Ising model in our field. So I think that we need to, we need to have much more discussions, but we need some dictionary between between machine learning researchers and also the theoretical physicists, because that I realized that there are so many differences, right? Spins and field and something like that. And I think that if we have some dictionary between the two fields, we can discuss much more efficiently.
Yeah, this is a little bit of an answer to the question about applications to experimental particle physics work that you may know. So, for example, David Shih and then collaborators at Rutgers have tried to do a model-independent search for a new collider physics by the device of training an autoencoder to compress standard model events, so things coming out of event simulations. And then the idea would be that events that don't compress and don't, the autoencoder doesn't like are, obviously candidates for new physics, and that seems to detect, simple models of new physics pretty well. And another person who's done a lot of work on model-independent searches using Bayesian methods is Kyle Cranmer. He's written many papers, of course.
Maybe a brief comment in response to Akio, and then I'll come over here. So something that our community has been talking about for a little while that we're making progress on, but not quite there yet, is having some sort of white paper where we try to explain what our data sets are, what our big problems are, etc. You mentioned a dictionary and wanting some sort of dictionary to be able to go back and forth a little bit. If anyone's interested in having some additional input, particularly from the ML side, for how to make that communication clear and useful, we would love that and are open to it. So just a comment.
I hope my question can be clear because it's a little bit vague, so I hope it makes sense. It seems some of the applications to problems in physics are like this selecting in the application to LHC, tracking. It seems a little more traditional to how you might do something in machine learning, where you might train something and then use it many, many, many times. But then some of the stuff where you might be trying to, say, extrapolate to count the number of these FRSTs, it seems like you're just extracting maybe one number in the end, or just a very few numbers, and you're hoping that this machine learning algorithm might help you predict some number that better. But why, perhaps, and this is kind of a philosophical question, I'm sorry, but why should one trust such better rather than asking, Wadi or one of these other experts in the field and say, well, you have this provable upper bound, and, what's your best guess where you actually think it is, So if we're just getting one number out or a few numbers out, why, what is the role of machine learning as opposed to a single human expert?
With regard to predictions for individual numbers, I totally take your point. And I think one of the advantages, problems where I can envision a strong advantage for machine learning type approaches is situations where there are a bunch of properties that we can compute given an individual example. So suppose we're talking about a reflexive polytope and a triangulation thereof, then in a matter of seconds we can evaluate all of these properties. But we might be interested in figuring out are there physical theories that enjoy certain properties? This might be an extremely rare property attested in 1 part in 10 to the 50 or something in the entire data set, and we'd like to search for them. So in cases like that, where people have made, for example, pencil and paper conjectures that there exist and there do not exist theories of a certain type, you can imagine figuring out what the truth is for those sorts of conjectures. These are things that in the physics literature go into the name of things like weak gravity conjecture, various forms of that make specific statements that are relevant for experiments and are relevant for the real properties of quantum gravity. And you can imagine trying to test those by getting a machine learning algorithm that will find for you relatively efficiently examples that you can check that may or may not be consistent with these sorts of conjectures.
Let me make a comment in response. So I think, to me, as somebody who's more from the machine learning side and knows a bit of physics, some parts of what I see kind of makes me queasy from the ML side, in the sense that, like, for example, you train stuff on Hodge number up to 10, and then you test on 11, 12, and 13. Maybe 11, 12, 13 is okay, but I will really be scared to look at the prediction at 500 and actually trust it in any reasonable sense. And I think I think we trust maybe physical formulas because it gives you a reasoning, right? It gives you a logic to follow. You latch onto it and it makes sense to you. But if you just have a bunch of weights, I think that's much less believable. And I think this equation learning thing maybe is a more proper way of doing it if you can give you interpretable models, which can give you a guess on what the right theory is, and then you can go take that guess and formulate it into a more formal kind of theory, which will take your prediction into like 500, and that gives you actually a reasoning behind it. I think that would make more sense rather than just try to get a machine that predicts something that you can't really trust.
Yeah, I would just follow up on that. I very much agree. I think, Matt, in response to your question, there are certainly cases where you have very large numbers of data, like 400 million of something, and you want to learn how to compute something that we may not have a precise way of computing, and you can test it on some, you can run it on some, and then test on others. But I think in cases where you're going to do a one-off, the real value there is if it can give you some new hypothesis about something we can understand that allows us to actually prove a new theorem or give some analytic argument for something. I agree with you. If you just do a one-off, it's hard to trust the answer without having something to compare to.
Maybe one more related question on this point, and then I promised Daniel a question. So this question about extrapolation is a very interesting question. So on this equation learner that you mentioned, so we do 10, 11, 12, and then, why should you trust anything at 491? One thing that sort of surprised us towards the end of the project is we said, look, we have this smaller data set where it's very similar in certain regards, and this does not explain the 4D result necessarily. I'm really asking sort of why it actually worked. We had upper and lower bounds. In that case, H11 goes up to about 40. And if you train it on low H11 at, and Brent made this point, sort of around 9, 10, 11, 12, and then you use that to extrapolate up and compare to the known results, what actually kind of surprised us is that it was actually doing reasonably well extrapolating. And any comments in general that people have about extrapolation from an ML point of view, we found empirically that it worked in our examples, but we were actually pretty surprised that it worked as well as it did in that three-dimensional case. So
amazing, and I think if I were a physicist and I'm looking at this, I would devote a lot of energy to understanding what the model actually learned and try to formulate that into a precise formulation. I see. Yeah.
Yeah, so on the comment on like one-off getting one number, so for example, there are still a lot of like topological numbers that are known to have bounds, but the bounds aren't precisely known. So we've seen 491 a lot, but there's another 491 that's just a conjecture, for example. Like if you look at two Hodge numbers of elliptically vibrated threefolds, one of them we know is bounded. The other one we know is bounded, but we don't know the number. So I feel like examples like AlphaGo has proven that machines can probe an entirely complicated, a very, very complicated, combinatorially almost impossible space very efficiently. So you can imagine training RL systems to probe a space and possibly hit a number that we haven't thought about before, or let it run for very long and find that, oh, it really can't go beyond the numbers we've found conclusively. So yeah, so I think it has the potential of even disproving previous conjectures, or even kind of giving more credence to certain bounds. We've tried with a self-playing RL system that tries to upper the bound by by some number, and we can't do it. So I think it's also useful in that way.
Okay, great. Thanks everybody for the comments. Oh, sorry, Renee, you have a okay. Well.
I wanted to follow up on your comment about interpretable models. So this is going to be a naive, maybe very stupid question, but has anyone taken all trajectories of particles and used neural networks to show that F equals ma emerges without knowing the physical equation, or then maybe Maxwell equations? Or so therefore, once you have a few concrete examples where you use no knowledge of physics and something emerges, that might give a pattern as to how to go about other problems.
Just as there was a big effort to do simple 4-vector math. So take two particles, combine, derive the invariant mass. So this is a very simple set of equations. Could we teach a neural net that? It was hard. And the equation was always better, especially if you the numbers that you trained it on, if you left those numbers and went above. So it seemed like the neural net wasn't actually learning the equations in this case. So
just add a comment. So one of my colleagues, Max Tegmark at MIT, has done some work with systems like that, where they have a physical system that obeys different laws of physics in different regions on a 2D space. In one place, it'll be obeying like an F equals ma with a spring constant. In another place, there'll be a force of gravity. And then they train a neural network to try to predict its motion. using a different law in each quadrant, for instance. And it actually does reasonably well at predicting the future motion and learning the different laws in the different parts. It's not exactly coming up with the equation, but that's one thing. Another thing, I don't, this is a little vague, so maybe somebody else knows better, but I think someone has tried to predict the future motion of a double pendulum. It may have been Max in his group or someone else, and had some success with that, which is a tricky problem.
So I know some people at Microsoft Research Asia, based in Beijing, has actually done exactly that. They try to learn F equal to ma, but the model is not. It's like neural network based, but he actually tries to learn a formula. So he actually tries to learn symbolic things, and then use the symbolic result to actually make the predictions. So that's a bit more different. That's more along the lines of like program synthesis or automated theorem proving. And I think personally, to make progress on what you mentioned before, to make progress on actually using ML to do physics. At some point, I think we need to reach this threshold where we have to make progress on doing neural automated theorem proving or neural program synthesis. And of course, Microsoft is very famous for being a very big research center for program synthesis and neural program synthesis. And I believe, actually, so last night when we had dinner with Josh and Mike, they had a bet against Clement and Boris. And Boris, could you relate the bet?
We were talking about automated theorem proving, or more precisely, theorem proof checking. And we made a bet that, well, I was on the negative side of the bet. I thought that within 10 years, there would not be sort of a commonly used system that really checks proofs that mathematicians write. I don't mean some kind of thing where you have a more or less simple formal system and you're just trying to play the game, but would check the papers that I write. That was the...
What's the dollar amount that you bet?
That's a secret. No, it was $250.
Is that inflation adjusted or no?
We didn't specify.
Is that in a specific subdomain or something general? I mean, would you lose the bet if somebody wrote something which just did it in a very special subdomain?
No, I mean in mathematics generally, somehow for mathematicians that are proving theorems.
Like completely generally?
Yeah, that's right.
I think we wrote it as like, outside of niche use cases. So define niche.
Yeah, I don't think we defined the bet as carefully as that. But I would take the bet that some class of natural language math papers, not certainly all, or even a big subset, but some well-defined class of papers that mathematicians find interesting, could be translated automatically into formal language, and again, to some extent verified. It might not get every step, but it would do a lot of it. So it's a little hazier, but that I would definitely predict within 10 years.
I can say that for my friends in the formal proof domain, that their goals are much less ambitious. What they're trying to do right now is get journals to require that mathematicians, when they submit papers, that the statements of the theorems be formally readable. So a formal system can at least understand what's been claimed. And if that can be implemented in 10 years, people will be very excited.
Yeah, not even to require, but just make it possible. That's right. Yeah. No, I was just at a meeting with Thomas Hales and Christian Szegedy at Google, somebody working on the thing that I was describing, and so it's definitely not going to happen within 5 years. But Thomas Hales' thing might start to happen within 5 years, and.
I think
the other thing I found fascinating in this discussion about the travails of teaching or asking a net to come up with F equals ma, et cetera, is it's human nature to give your talk about what worked and not give your talk about what you were unable to do. But for me, the most interesting part about ML and neural nets is where they're having trouble. That's actually what fascinates me, because that's a kind of a wedge where you wonder whether a quantum attack might help, or perhaps a different architecture. So it's hard to. I just encourage people when they give talks to emphasize that side of the subject as well, because I usually just hear about it informally.
This is a nice segue into a discussion on, like we had talks in the first half, day one of the workshop on understanding neural networks, and Mike brought up a very good question of understanding how they fail. So any comments, for example, on Joshua's talk on the first day, and Clement and Rio on understanding neural networks? So any I guess, what do we learn? What do we learn from these talks on the first day? So
I'm sort of looking forward to hearing more from Joshua about how the linearized problem is not as successful as the nonlinear problem. I mean, it seems like you've got this very powerful, beautiful framework to really analyze the linearized problem, and you're saying that it's missing something. So if you can quantify what it's missing, A, what it's getting, and B, what it's missing, I think will be a huge step along.
This is exactly a thing that we are very actively researching right now. I don't have a good answer for you yet. I can go on some hand wavy extrapolations, but maybe this is talk to me later and I'll give you some hypotheses that are probably all wrong.
So I can comment on this particular question. I think for me, I mean, Joshua, you can disagree with me, but I think for me, probably the linearization, the regime in which linearization fails is when you try to train your linear nets using a large learning rate, and this is typically done in supervised learning, where so for those who are not familiar with training on ImageNet or state-of-the-art data sets, but usually use a very large learning rate, and then you drop it at some point after it has kind of not gone down for 10 epochs, and then you drop it again when it's becomes stationary again. And this is, I think, in my observation, it's a very different dynamics, especially when you add batch norm advanced techniques like that to the dynamics of the actual small learning rate regime, where the linearization actually holds quite well.
So I think that the behavior in the large learning regime is super important and super interesting and one of the aspects of this problem. But we find that we have difficulty getting linearized state-of-the-art architectures to 100% training accuracy using standard training techniques with any learning rate. And so these are architectures that are massively overparameterized. So it is clearly physically possible for them to exactly fit the training data. So I think the nonlinearities you might encounter at very large learning rates might go some way towards explaining the differences in generalization gap, but we're not at the point yet where we can say something about the differences in generalization gap, because we have a basic difference in trainability, which is still a bit of a mystery.
Okay.
So I think the question of discussing cases where neural networks fail, it's a very important one. And so I was very skeptical in 2012, and it was working impressively well for classification problems. And then I said to myself, it'll never work for detecting objects in an image. And 2 years after, they produced the best detection results. Then I said, okay, for problems that there are more relationships, like segmenting an image is not going to work. And then surely 2 years later, outstanding results were produced. So in my view, what are cases where it works? It is cases where there is a great match between the architecture design and the structure of the data. And so images is one example where all of these hierarchical convolutional architectures are well matched to the hierarchical relationship between whole objects, part of objects, and local textures that emerge in images. But even for computer vision problems that require more intelligence and more contextual relationships, I think they fail. Namely, if you really had to reason about fairly complex spatial relationships of objects in an image, I don't think that neural networks have achieved really true intelligence, in the sense that there are puzzles that we humans can resolve, but those architectures cannot. Then when it comes to cases where discovering physical relationships, I think there is a need to put together physical models with or phenomenological models with learning. I think cases where there is a mismatch in the problem with architecture, I think I already mentioned that. So I think there is a lot to be done, and it's not just the theoretical understanding of why and when it works, but I think when it comes to really relationship with problems, we need to think. I think architecture design is done by hand today, and so figuring out how to automate the design of the architectures for every specific application that doesn't fit the pattern of images is one challenge.
I would like to continue what René was saying, and I want to point out two things about neural networks. First of all, they are not causal. If we change the input distribution, we are going to learn a different model. And the second thing is that in the sciences, accuracy of prediction is not, so what we believe the scientifically correct model is not always the most accurate. And so neural network which optimize the prediction error are very likely to produce accurate predictions, but not models that transfer to other situations. For basically, they don't incorporate causality and they optimize on the output. And that's all I have to say.
So maybe I'll just follow up on what both of you were saying, but coming back to your statement about the architecture matching the problem. I think for me the thing that really raised my eyebrows was AlphaGo 0, where it doesn't seem to me that there's a natural match there between the problem and the architecture. It's sort of like a computer vision problem where you really need to think about what all the pieces are going to do in the future. So would you say that in that case there is a good match between the architecture and the problem, or how would you fit that into the paradigm that you described?
Yeah, I was looking for my words, and that was the other example I was going to give, and I hope Pratik knows the example better than I do. But my understanding is that it's not clear to me that in AlphaGo they really learn how to do the game and how to play, versus whether they just memorize all the patterns that show up in the images.
So I think AlphaGo itself was like what you just said, but AlphaGo 0, which learned from scratch, I think must have been learning the latter. But
I'm not sure I know the answer to that question, but yeah, so there is a big difference between AlphaGo and AlphaGo 0, and it is indeed extremely mind-boggling why AlphaGo 0 works. I don't know how to explain it. AlphaGo by itself, yes, that looks like a system where you have built a very good engineering side for doing Monte Carlo research well, and then there is a supervised aspect to it where you evaluate each node properly. AlphaGo 0 is something that many people, including me, are trying to understand. It does work. It works for chess. It works for Go. We don't know why. It is one comment I would like to make in the context of architectures and problems is for problems like vision or text or speech, it has good architectures have emerged through natural selection or graduate student selection. And it is by now considered like a closed case. So you know what architecture to pick if you want to do image classification. For reinforcement learning, there is no such architecture. All the networks you will see are basically things that are small enough that they work, large enough that they are interesting. So that question is quite open in RL, and which is probably why RL doesn't work as well as computer vision today.
Can I just ask a follow-up question to you on that? I always imagined that AlphaGo worked by something close to facial recognition, because Go seems to depend on this sort of topological idea of surrounding, and I just thought it was a very visual concept, and I assumed that facial recognition techniques just would naturally flow over to that domain. Is that accurate or not?
Faces are very easy. So even before deep learning, let's say in the early 2000s, you could do PCA on a face dataset and build real systems that work at the scale of large companies. Go seems to be a much harder problem, right? Because the number of states in the system is very large, even though it is primarily visual, as you say. It's the patterns that AlphaGo plays, even AlphaGo, are like completely beyond what you would play as even an intermediate player. I think, yeah, so faces, many vision people would agree, are just genuinely easy. Detecting instance recognition, so identifying one person out of 1,000 is harder, but classifying people between, like, let's say, genders or age are problems that we have been solving for a long time before deep learning.
Well, no, I understand that faces are easier, and I know that AlphaGo beats all human experts, but what I'm thinking is that if you compare Go to a number theoretic problem like factoring, it seems that it's much closer to, the bread and butter where ML came from, of facial recognition. It just seems that it's a visual domain, and the patterns that are useful. It's basically, as I understand it, the important thing is to be able to evaluate a landscape and know whether adding a stone somewhere improves your position a little bit or a lot. And so it's basically evaluating an energy functional on a picture. Whereas if you're trying to factor a number, I just think that ansatz, doesn't apply at all.
So just briefly, I mean, there are very complicated non-localities in Go. Like there are these ladders where if you're on one side, you play a thing here, it'll affect something way over on the board. And it's true that it took AlphaGo 0 longer to learn those than typically it does a human. So it's a little slower at long distance things. But I mean, it does seem like it's done something a little bit that seems a little miraculous. I'm just curious if you have any insight into how to take whatever was done there and apply it in any other domain, like some of the math physics we've been talking about.
I just wanted to maybe one comment about applications. So AlphaGo has like an extremely impressive like neural network based value function inside it. But the thing that makes AlphaGo like completely unbeatable is that they are using this like neural network within a Monte Carlo tree search scenario. So they have an algorithm for playing the game, which has like various guarantees, at least in the limit of infinite compute to start with, and then they are using the neural network not to like play the game on its own, but they're using the neural network as a component to like improve the evaluation of leaves within this algorithm. And so maybe it suggests that a really good way to get very, very strong results out of neural networks is to take some kind of system, I mean like Monte Carlo for instance, and use the neural network to like adjust the proposal distribution rather than use the neural network to like scrap the entire system.
So let me make a comment first. So there's a reason that DeepMind did not open source AlphaGo or put it online for everybody to play, which is that RL systems are usually actually quite brittle, and there's a pretty high chance that it's actually if you like play against 1,000 times or something, you can learn like a trick against it. And because it's not a learning system, it's not an evolving system, you'll be able to beat it consistently. For example, like recently OpenAI had this Dota bot, which made some news, and he beat a lot of humans, but I think some teams figured out a consistent way of beating it after OpenAI actually opened it up for the publics to play against it. So this is a very ongoing question, research question, which is like, how do you prevent against adversarial attacks or even just like brittleness in the learning algorithm? And this is a very important question when it comes to like self-driving cars and other things are actually critical to our safety.
Yeah, I just want one quick comment, and that's actually one of the reasons in my quick talk that I focused on this Joseki, because that's like a math theorem or something. It's like a piece you can take out, and even if it's a brittle system, it's still found something new that's uncontroversial. Sorry.
So to follow up on Joshua, I think one important aspect in the entire AlphaGo reinforcement learning area is that so these methods are extremely data hungry, and they work exactly then when data is cheap. And so in all these kind of games, right? So when you can simulate a lot of data and very easily kind of come up with millions of ways to evaluate your cost function and kind of improve on yourself, then these methods work really well, apparently. And this is like Atari, this is Dota, this is AlphaGo in that sense. But if you're in a domain where it's hard to get data and where you cannot very easily simulate new stuff, then it's much harder to apply.
So just, I mean, Mike...
And in that sense, in AlphaGo, actually the model so the architecture fixed the problem, right? So because it's cheap to get the data and then it works.
Right. So one of the great things about physics and math is we've got all these Platonic data sets, as somebody mentioned yesterday and Mike was alluding to. There are lots of data sets that you can just generate for free as much as you want.
So,
yeah, I'll make a couple of comments. I mean, about the AlphaGo and the analogies with math. I actually had this coined this Platonic data set in my talk yesterday, and so there are analogies and differences, and definitely math has this ability to generate arbitrarily large data sets. And another kind of loose analogy is that like Go and unlike chess, you know, it's pretty much always positive to make a move in math. Making a move is saying, proving a theorem, or putting a statement out as relevant for your considerations, and that's a positive thing. And in the game of math, you often do place a theorem out pretty far as a goal and try to build towards it and so forth. And then of course, many differences that it's generally not thought of as a competitive sport in quite the same two-player way as Go, and it's really not obvious what the objective function is, and it's in this far, far higher dimensional space, which we don't know a priori. A big part of the game is just to explore the space and map it out in any kind of way at all. So, but that's certainly. I think the similarities and the existence of this, its Platonic nature is a reason to think that math's going to be one of the earlier domains where AI and ML achieve some sort of reasoning capability. And then to totally switch topics and come back to Josh's talk and some of the other talks. I mean, these questions about how AlphaGo works and what are the range of tasks that it can work with are just so far beyond anything we understand, and it just has to be studied empirically in terms of proposing other tasks which are sufficiently different that we can learn. But even these basic questions of how very simple feed-forward networks generalize are not really very well understood, is my understanding from the literature and what I hear. And so the kind of models that Yasha talked about with the infinitely wide limit are very attractive to have models that you can solve and then try to understand it. And so I would certainly be very interested to see results on generalization coming out of that framework and explaining the graphs he had in the first slide about a width versus generalization, other parameters versus generalization. I think that's still a key problem that people are not satisfactorily understood.
So coming back to this question of what types of problems are suitable for deep learning to solve. And I think one key characteristic that a problem can have is that determines the suitability of deep learning is really the sort of description length that you expect the optimal model to have. If it's a very short description length, probably current deep learning methods are not very suitable. If it's very large, then I think often deep learning is the tool you want. So for example, visual recognition is clearly a case where you need to extract a lot of bits of information from your data set into your model to be successful. Language, interestingly, is another example. We all learn in school a couple of rules of grammar, and that's supposed to explain how language works. But the reality is that it's one big bunch of exceptions, and you need to have a lot of knowledge, a lot of bits of information to successfully use language. Go is another example where there are some theories that experts have about how Go works that are fairly low description length, but still, even professional Go players, they say that they're using a lot of intuition, i.e. there's a very big model required to do well. Something like F equals M times A is extremely short description length. So that's not something a deep network is going to do. Or rather, it's going to be very good at matching that equation, but it's always going to do it by a sequence of linear, nonlinear maps with millions of parameters that eventually simulates this thing, but in a way overcomplicated manner. And maybe one more thing that's related to that is this issue of adversarial samples. There was a very interesting paper. I think Joshua was on it as well on adversarial spheres. No? Okay. Anyway, people related to Joshua were doing this. I forget who it was. And so they were investigating the problem of adversarial samples theoretically using a data set consisting of two spheres in high dimensions, a big sphere and a small sphere, and you have to classify which one it is. Concentric, yes, correct. And the way a deep learning model is going to approach that is it's going to try to have little facets everywhere on this very high dimensional sphere, trying to build a decision boundary, whereas a human maybe would look at it and see the length is the distinguishing feature, and once you recognize this, you have this very short description length model that generalizes perfectly, is invulnerable to adversarial samples, and gives what we call insight. And so that is something I think is a very interesting challenge for deep learning, to sort of adapt the capacity of the model down if possible, or as in the case of language, to sort of extract a simple theory that still explains relatively much of the data, even if there's still a lot of exceptions out there.
Allow me to connect your question on number theory with Zasha's answer on robotics and expand upon Taco's answer about model complexity. I think one word that we haven't mentioned yet, and we've been basically going around it forever, is the issue of input representations of data. So problems like, let's say, checking, I talked to a bunch of string theorists yesterday and know like the first line of Wikipedia now about string theory, but coming up with a good representation for feeding this data into a machine learning model is the hardest hardest thing to do in these discrete problems. In the robotics world, we are good at using certain kinds of data, so point clouds, images, etc. As soon as you put in some domain information, so AlphaGo uses Monte Carlo tree search. In a robotics world, I would do something like motion planning in addition to some amount of deep learning. Things start working. So the model is one thing. The hardness of the task, as Taco talked about, is a third thing. But the input representation is something that we don't understand. Maybe instead of doing fMRI on images from fMRI, the right data to use is simply all the signals that you get before the images were created. Images were created for human doctors. Maybe a machine needs the different kinds of data. So it is still unclear what the right way to represent all kinds of data is. It is I am convinced personally that deep networks can't handle any which data you give them. They like their data in a certain kind. So I like to say colloquially that they like data that is very large and very dirty instead of having data that is very small and clean. For instance, time series versus videos or time series versus images. And this is something that most practitioners will sync with.
Let me comment on from the physicist side. So many people mentioned to the F equal ma, and even even if we know the fundamental equation of motion, for example, F equal ma, but if once we add degrees of freedom inside, we cannot solve it exactly. And so at that case, we generate a bunch of data and analyze that bunch of data by using some sophisticated way, and even in the classical mechanics. And now we are trying to understand our quantum world. That situation really bad because that everything is stochastic, and so we have to solve the Schrödinger equation to determine the future distribution. So for that purpose, I think machine learning is had a good technique to analyze our world, including quantum mechanics, not only the quantum mechanics, but also the quantum field theory or quantum gravity.
Great. So that seems like a natural conclusion to our discussion session. There's food outside. But before that, let's take a couple minutes to introduce the breakout sessions that are going to follow. So there are going to be two sessions. Each session has 3 parallel tracks. And let's have all the breakout leaders come up to front and give a couple words on what is going on and what's going to happen in the breakout sessions.
Yeah. So Mike and I are leading one of the breakout sessions on the string landscape, and our thought really at this point was to have an open conversation that sort of follows up on the issues that both of us raised in our respective talks, and particularly give people from the machine learning community a chance to push back on the various proposals that we made and try and develop something at that interface. But we didn't have anything particularly structured. We were hoping it could be free-flowing.
So my name is Sergey, and Yang Hui He is here. So we'll be leading a session on symmetries and their realizations in string theory. So hopefully this will be a natural continuation of discussion of symmetries both in machine learning as well as in physics. So we expect that please come and ask questions both ways.
Hi, everyone. So Yasaman and Jaehun and I are organizing one of the ML breakout sessions on understanding deep learning. And we were kind of thinking of structuring it by having just a very quick crash course just to introduce some notation and how at least we think about how deep learning is set up, and then open it up as much as possible to just trying to discuss what we think are some of the interesting theory problems that one could solve, try to solicit some problems from people in the audience if you're already experts, and then just try to have some kind of discussion of what some ideas might be to solve them, or maybe what some experiments might be to clarify what the problems would be that we should clarify.
Hi, my name is René Vidal. I'm leading one of the sessions on optimization and physics. And I'm by myself, so if anyone wants to help me, that'd be great. Otherwise, maybe we can join the theory of deep learning since optimization is part of it as well. I think the main point is to discuss how insights from physics, such as Hamiltonians, can help the design of faster and better optimization algorithms, as well as how optimization can help solve some of the problems of physics.
Hi, my name is Yizhuan Yu, and I'm with Hashimoto-san. We will lead a discussion of machine learning holography. We hope to discuss, introduce holographic mapping to machine learning experts about I think it's deeply related to geometric learning and representation learning. And we also want to learn from machine learning experts about what are the architectures that we can use, or what are the most advanced technology that can possibly be applied to these problems.
All right. Yeah. So hi, I'm Max. Yes, I'm going to lead a session on geometric representations in, it's called deep learning, but I would say machine learning in general. And this covers a bit the topics, what I talked about, what Taco talked about, also what Marina talked about, manifold learning. And so the idea is to give like a rough overview over the field and then open it up to discussion. And it would be great to get input from physicists on what kind of techniques could be interesting in that field, and also to see how these methods are applicable in a physics context.
Where will the breakout session be? Yes, very, very timely question. So one breakout group will be in here, and then we have two neighboring rooms, which are going to be a bit smaller. But so we'll have one room for each breakout group, and we're going to put some piece of paper outside or something to indicate which one is which. So okay, feel free to get food, fill your stomach. So the breakout starts at 1:30? Yes.